Now let's tie things together. We've looked at IR, we've looked at mass spec, we looked at proton NMR and carbon NMR. Let's tie them together. We'll combine IR and both types of NMR spectroscopy in these examples, and I'll show you how you can go through these and actually get all the pieces of the puzzle and then put that puzzle together and get your structure. So let's take a look at an example here. And so we'll start off with this compound. This is C8H10O, and I'll show you how to tackle these problems. So again, you can go into this with a molecular formula, because that formula is obtained from both the combination of a mass spectrum and an elemental analysis. So it gives us a little piece of information. Now what we can get from the IR, we are kind of limited. We go for the functional groups here, the types of bonds. One of the first places I like to go is that 3000 line. And look at that 3000 line. It's very important that you look on both sides of it. On this side you're going to find hydrogens and carbons. Hydrogen-carbon stretching where the carbon is sp3 hybridized. On this side is where you'll find carbon-hydrogen stretching where the carbon is sp2 hybridized. Always distinguish between those two. And sometimes you can overlook this guy. And see over here, we've got a very broad absorbance. Remember, broad absorbance usually is an indication that you have some hydrogen bonding going on. And this one's centered at around 3300. So I'm thinking either an alcohol or a phenol. So that's our OH bond right here. We're not seeing any carbonyls showing up here. However, we do have a little bit of aromatic overtones. They're subtle, but I'm going to guess that there is a aromatic ring in this compound. So we've kind of dissected our IR as far as we want to go. We don't want to go into it in any more detail. Dive into the NMR next. So we know we have probably some double bonds in there and an OH. So now we can take a look at our proton NMR and our carbon NMR. And notice we do have things showing up at around 6.5 to 8. That's the aromatic region. That's where you say to yourself, there is some aromatic hydrogens here. And we're going to start doing our accounting as well. So we know that we have 6 carbons and an aromatic ring. That takes up most of our compound right there. But how many hydrogens are on that aromatic ring? The integration tells you that. And in this type of spectrum here is actually giving us the integration. That part's worked out. So there's 2 hydrogens in this signal, 2 over here. That means there's 4 hydrogens on the ring itself. So C4 or C6H4, and that just leaves us with 2 carbons, 6 hydrogens, and an oxygen. And so if you have 4 hydrogens on your ring, that means the substitution pattern has to look like one of these 3. Either the 2 substituents are next to each other, a little bit farther away, or on opposite sides of the molecule. Now if we take a look at this even further, so if it was this compound right here, we would expect to see a hydrogen giving us a triplet in the aromatic region. There are no triplets there. Same thing over here. I would be expecting to see a triplet. Based on that, I have to rule out this structure and this one. This is one of our puzzle pieces here. This is a 1,4 di-substituted aromatic ring. And a typical giveaway for that, if you have 2 groups that are very different on there, is you're going to find that you'll have a pair of symmetrical doublets. And one thing I want to also point out, these guys are leaning towards each other. Notice the inner peaks are a little bit taller. When peaks are coupled to each other, they tend to lean towards each other. Another little piece of information there. Now, from our IR, we determined that there was an OH. We can find it right here. That's that nice broad absorbance. We see line broadening due to hydrogen bonding on NMR spectra as well. It's really a function of how wet the sample is. Water will have a big effect on this. The drier the sample, usually the narrower that signal. But if you see a broad signal, think hydrogen bonding. And let's take a look over here. But actually, before we do that, let's take out our other puzzle piece. So if we take out that hydroxy group, that leaves us C2H5. And here's what we're going to do with that. We've got a 2:3 ratio, and we have a quartet and a triplet. That is the signature of an ethyl group. And that uses up all the pieces of our compound. This compound has to be this one right here. So we actually figured out most of our structure just from the proton NMR. But let's explore our carbon NMR too. That gives us a lot of good supplementary information. Sometimes you can use it to break a tie as well. So remember right here, this is where you find your CdCl3. So your ethyl group, there's your CH3 group, there's your CH2. Then we have 1, 2, 3, 4 types of aromatic carbons. Remember, there's a plane of symmetry running through this compound. So this type of carbon is the same as this one. And I'll put little squares around here. Those two guys are the same. And so we've got 2 big carbons, 2 small ones. The 2 small ones have to be the quaternary carbons, the ones that actually have no hydrogens attached to them. And you might be wondering, how do we figure out who is who? And guess what we do? We do a little bit of resonance. Resonance will help us figure out which peak goes with which carbon signal. Turns out I can resonate, and I can put a partial negative right here. I can put a partial negative here. Partial negative means shielding. That means upfield. So this small signal that's upfield has to be this guy. The small signal over here has to be this one. This signal has a partial negative, which is shielded. Has to be this one. And that leaves just that signal right there. So we can definitively assign which carbon goes with which signal. Same thing up here. This doublet right here has to be the one that's closer to the hydroxy group, because you can put a full negative charge on that carbon. So we have dissected this spectrum as much as possible. But remember, put those puzzle pieces down. This is a deductive reasoning puzzle. And any day now, the local newspaper is going to put one of these, next to the Sudoku. You might have the daily spectroscopy puzzle. I'm waiting for that. Let's take a look at another example. Here's C10H14. So just hydrocarbon. And here's that all-important 3000 line, which tells us we have a couple of types of CH bonds. Both sp2, sp3 hybridized carbons, and this one is a very, very well-defined aromatic overtone region. There's definitely a ring in here. And if there's a ring, the CC double bonds tend to show up right here and here. So we've got some puzzle pieces, but we don't dwell too much on this part of the puzzle. Now we move on to the proton NMR. Proton NMR, we again see between 7 and 8 we have some signals supporting our choice of aromatic ring. And take a look at this. 5 hydrogens on that ring. That tells us that we have a C6H5 group. That's a phenol group. And that also tells us that it's monosubstituted. That's a piece of our puzzle right here. And we can't really see all the splitting very well, but it doesn't matter because our integration tells us that there are 5 hydrogens on the ring. This must be monosubstituted. So that only leaves 4 other carbons to deal with on this group here. And we have different choices here. When you get down to just a few possibilities, don't be afraid to take out a piece of scratch paper and draw those possibilities. There's only so many things you can do with 4 carbons. And let's do those things. So I can draw a butyl group if I wanted. I could draw the isopropyl or isobutyl group. Let's see, the sec butyl group or the T-butyl group. And watch what we can do with these right away. We look at the T-butyl group. Every one of these CH3s is in the same environment. The dead giveaway of a T-butyl group is that you tend to have a giant, actually a ginormous signal that isn't split, that integrates for 9 hydrogens. We do not have that here. We've got 4 different signals. I have to cross this out. Likewise, over here, there's a little bit of symmetry. So this is very symmetrical when you have the T-butyl group. This one, there's still a little bit of symmetry with an isopropyl at the end. This carbon is the same as this one. So this would be 1, 2, 3 types of carbon. We've got 4 types of carbon, 4 types of hydrogen here. I have to cross this out. Now I'm down to 2 possibilities. And so here's where I can rely on integration. Let's take a look at this. I've got 2 hydrogens, 2 hydrogens, 2 hydrogens, 3 hydrogens. This is a 3 hydrogen signal, 3 hydrogen signal, 2 hydrogens, 1 hydrogen. I have to cross this guy out too. So those integrations are really key to figuring out these structures. So if I look here, I've got 3 hydrogens, 1 hydrogen here, 2 hydrogens, 3. That'll match things up. And we haven't even explored the splitting pattern yet. So let's do that. So we've got a CH3, CH3, there's an H right here, and 2 hydrogens here. So one of my CH3 groups has 2 neighbors. So this is going to be a 2 hydrogen triplet. That is this signal right here. The other CH3 group only has 1 neighbor. He's going to be a 3 hydrogen doublet. And a way we would actually indicate that is we're at 3H triplet. This would be a 3H doublet. And we look at this. There's 2 hydrogens here. 3 neighbors on one side, 1 on the other. That's going to roughly be a pentet. And that leaves this hydrogen as 3 neighbors on one side, 2 on the other. It gives us this multiplet or sextet over there. Those are all of my groups right there. So again, we were able to figure out the structure using the proton NMR, but we can still use our carbon NMR to really firm things up and to make us totally sure of our answer. So if we look at our carbon NMR, we've got 1, 2, 3, 4 types of carbon. And that's actually what we see over here, 4 types. We can't really assign who goes who right over here, or who goes where, because these are all very similar. But we can say pretty surely that carbon number 1 has to be this guy, because he's very small, no attached hydrogens. Other than that, we can't really read much into these signal sizes here. So you got a little bit of solvent right here, and then we have these 4 carbons corresponding to these 4 carbons. So it kind of backs up our choice here of structure. So that's for a hydrocarbon. Let's see, let's take a look at our next structure. So this one's C9H10O2. So we got a couple oxygens showing up here. Now one thing I want to point out here, we have a pretty well defined carbonyl. So we got a CO double bond. That can account for one of our oxygens. The other thing we have is a very broad absorbance that goes from about 35 to 2500. That is the OH of a carboxylic acid, which is a very broad absorbance. and it even covers up all of the carbon-hydrogen stretching. But the carbon-hydrogen stretching is still there, some on either side of our 3000 line. So both types. And we can even see a little bit of aromatic overtones here. So this one's probably a carboxylic acid. That's what's going to be one of our puzzle pieces. So pretty useful there. And something else we can get just from the molecular formula, we can actually tell how many pi bonds are here. And also, if we have a ring, how much unsaturation. So a little bit about unsaturation and what we can glean from our formula. So if you have a compound with 9 carbons in it and it's fully saturated with hydrogens, remember that formula, CnH2n plus 2. We would expect to see 20 hydrogens here. We only have 10. So let's do a little bit of accounting. C9H20 minus C9H10. So that's what we have in our compound. This tells us we have a difference of 10 hydrogens. That means our compound is unsaturated. We don't have as many hydrogens crammed in there as possible. That means one of two things. We either have pi bonds or rings. And so every degree of unsaturation is due to either a pi bond or a ring. And a degree of unsaturation is worth 2 hydrogens. So this is 5 degrees of unsaturation. So we either have 5 pi bonds or 5 rings or some combination. We know one of the degrees of unsaturation is due to that pi bond. The other 4 degrees of unsaturation will probably be from an aromatic ring. 1 degree from the ring, then 1, 2, 3 from those pi bonds, and then the CO pi bond. So we've got 5 degrees of unsaturation. So you can learn some just from the formula. Oxygen will not affect those degrees of unsaturation. So now let's dive into our proton and carbon NMRs here. And so we know that we have an aromatic ring, and it has to be mono-substituted based off of this right here. And it's going to give us C3H5O2. And we can't see what's going on with the splitting. It doesn't matter. This is mono-substituted. We have to have something, one substituent on that ring. And we just have to deal with three of our carbons now. One of those carbons is actually a COOH. So here's 2 of our puzzle pieces. Let's also take out the CHO2 and see what that leaves us with. 2 carbons and 4 hydrogens. And let's take a look at our splitting over here. We have 2 triplets. So these guys are neighbors of each other. And so this guy has 2 neighbors. He has 2 neighbors. Let's put the neighbors together, because neighbors got to be neighbors. And that's our third puzzle piece. That takes care of 2 carbons and 4 hydrogens. We have a 3-piece puzzle. We actually have 2 methylene groups next to each other. So this compound has to be this guy right here. And we can see the OH up here. And we also see that our signal is actually kind of small and it's very broad. So we see that with carboxylic acids. And if you look on your correlation table, you'll see carboxylic acids between 11 and 12. That's if you have an ideal sample where you have it very dry. But a lot of these hydrogen bonding groups can vary in where they show up, so be careful about that. It's showing up where you would expect an aldehyde to show up, but aldehydes tend to be very sharp. And let's explore our carbon NMR. So here's the carbonyl carbon. And for carboxylic acids, they tend to be right around 180. And then we have 4 types of aromatic carbons. 1, 2, 3, and 4 showing up in this region. One of the small ones will have to be that signal there. And then we have our other 2 carbons showing up here. And again, our carbon NMR is consistent with our proton NMR. So, and that's what you do. You put those puzzle pieces down on paper. So whenever you see a puzzle piece, put it down. The structure will not just jump right out at you. Let's see. And one other thing I want to show you, just another example. This is a long chain compound. This is actually octanol. 1, 2, 3, 4, 5, 6, 7, 8. And sometimes with these long chain compounds, you don't get very good resolution in your proton spectrum. In fact, we have a lot of overlap here. So if we start here on the shielded side, we do have 3 hydrogens. It looks kind of like a triplet right there. That's this guy all the way at the end of the chain. And that's common that you'll see that at the end you might be able to see that triplet. This signal right here is our most downfield signal. That's normal for saturated alcohols. And so this one gives us some splitting. We can't quite tell what's going on there. Is it a triplet? Is it something a little bit more? The splitting here, so when you have a hydrogen bonding group, they usually do not participate in splitting. This is what's called an exchangeable hydrogen. And because it undergoes intermolecular hydrogen bonding really well, it tends to not always be present on the molecule. And so usually it does not experience splitting. But sometimes it does. And they can be hard to nail down. Sometimes they'll move around quite a bit. But for a non-aromatic species like this, that's an alcohol, usually the second most downfield is going to be your OH. After that, we're going to see lots and lots of overlap here. We can't tell what's going on as far as splitting. And so we can't really delve into it too much there. This one we actually have to rely on our carbon NMR to tell us that we have 1, 2, 3, 4, 5, 6, 7, 8 carbons there. The farther away from the oxygen, the more upfield they are. So sometimes that carbon can actually tell us more information than the proton NMR. So that's been a few examples. What I want you guys to do now is try some of the problems in your textbook. Chapter 14 has a wealth of NMR problems, and practice will make you more and more comfortable with this. And so I'll be signing off, and it does appear that that rogue NMR unit has not been seen for a while, so that's good. Uh-oh, I better sign off. Here he comes.